To help set the stage for what this class is going to be like, I want to tell you a story. Here's a triangle. It's got some sides. It happens to be a right triangle. And because it's a right triangle, we have the Pythagorean theorem that if I square each of the sides, or at least their lengths, rather, and then I add those together, I get the square of the length of the hypotenuse. This is probably pretty familiar. You learn it way back when. But did you ever wonder how we know that that works? Like, how do we know that no matter what triangle you give me, as long as it's a right triangle, this will always work? You can always square those sides, add them together, and you're always going to get the square of the last side. I mean, we didn't test every triangle out there. That's impossible. Surely there's infinitely many triangles. Surely someday I'd be able to find one that doesn't work. But actually it does. I mean, if you think about it, this is kind of weird. Squaring would usually tell us something about area, but this is telling us something about the side length. So why does this work? So there's a lot of mathematics behind why we know this works every time without having to try every possible triangle. I won't go into those arguments here, but this particular result, the Pythagorean theorem, has tons of proofs out there, some of which are very simple and easy to understand, and have a lot to do with area and explain why there's a square in there. So if you just Google the Pythagorean theorem, you'll find some really great videos and articles out there about it. But let's keep asking some questions about this. Okay, so I have this formula, and as people, as humans, we like whole numbers more than we like fractions and decimals. So the question is, can I make this equation work with just whole numbers? This might also feel familiar. For example, 3, 4, and 5. If I take 3 squared plus 4 squared, I'm going to get 9 plus 16, which is 25, which is 5 squared. So 3, 4, and 5 are what we call a Pythagorean triple. Cool, okay, so I can do it. Great. Well, the next question is, how many times can I do this? Is there some list out there that stops at some point? That, like, this is all of them. This is all the examples where you can do this. Or does the list go on forever? Can I always find another example? Well, using some basic algebra skills, I can multiply both sides of my equation by something and it's still equal. So I can multiply all three of my numbers by 2 or 3 or 4 or 5 or 6 or 100 or a million or 17 or whatever, and I get another Pythagorean triple. So that list goes on forever because I can always multiply by another number. But that kind of feels like cheating, right? Like in some ways, this really only counts as one example, and then I've just multiplied it by a bunch of different numbers. Okay, so let's do that. Let's say that whole list, that infinite list, that counts as one. It's just, and then a bunch of copies of it. Okay, so if we count that way, now how many examples are there? Well, here's a few. There are more than one, but this is just a list that I can write down. This doesn't tell me how many there are. Does this list go on? Are there more? Are there always more? And it turns out the answer is there are infinitely many. No matter how many Pythagorean triples you write down, there's always another one out there that is not a multiple of any of the ones you already have on your list. The proof of that one is a little bit more complicated. Again, you can Google and find lots of great resources. I'm not going to go into depth with it right now, but you should know that the argument is out there. Let's keep playing. Let's look at the equation again. It started having to do with a triangle, right? We wanted to measure this information about the sides of a triangle and how they're related to each other. But even if we separate it from the triangle part of it, it's still just a perfectly fine equation. So let's just play with the equation. I have a squared plus b squared is c squared. What if I change it to cubes? A cubed plus b cubed equals c cubed. All right, I've totally lost the connection to the triangles now because I've changed the equation. But it's still just a perfectly fine equation. So let me ask the same question that we did before. Can I find whole numbers that if I cube them and add them, these two of them, then I get a perfect cube? And why stop at 3? What about if it was a 4th power or 5th power or a 7th power or a 100th power? Can I find these examples? And if I can, how many are there? So the Pythagorean theorem, the original one having to do with triangles and right triangles, this was known in ancient times. That's actually how the ancient Egyptians built the pyramids. So that's been around for a long time. This question here of can I do whole numbers if my power is bigger than 2, this question was first asked in 1637. And we didn't know the answer until the 1990s. It took 3.5 centuries for mathematicians to figure out the answer to this question. That's a lot of time and a lot of really advanced mathematics that went into solving what feels like a simple question to ask. It turns out the answer is no. For any power bigger than 2, there are no examples where all 3 of the numbers are whole numbers, unless of course 0 is one of them, but that doesn't really count because it sort of just turns into a different equation. If I really want to have like 3 and 7 and whatever, you can't do it. But the question comes up again, how did we figure this out? We didn't test every number out there. That's crazy. It's impossible. And it might feel like, but there's infinitely many numbers. How are you telling me that I can't just find one of these infinitely many that works? None of them work. There's a lot of fancy math that goes on to prove this one. It's called Fermat's last theorem. It was proved by Andrew Wiles in the 1990s. And a lot of really brilliant mathematicians don't have the expertise to understand his proof. Thankfully, there are ones who do. But I'm not going to go over the proof of it because it's not my area of expertise. I don't understand his proof. But it's out there. Someone has proven it using fancy mathematical, logical reasoning. Okay, so you might be wondering, why did I tell you this story? What does this have to do with this class? Well, the first answer is that there's always a why behind the results that we have. Right? Every time I told you, well, this is why, this is how this works, and this is, we have the Pythagorean theorem. Why do we know that that works? There are infinitely many examples of Pythagorean triples. I didn't tell you what the why is, but I told you there's a why out there and you can go find it. Every result that I give you in this math class will have a why behind it. And we're going to talk about the why a lot. But even if I don't tell you why, or give you exactly the right why, there is a why out there, and I would love for you to ask me what it is. We played a lot of this what if game. What if I only counted this list over here as 1 because really they're all just multiples of the same one? What if I change the equation? How does that change my results? We're going to do that a lot too. That is like the real like hands-on doing of mathematics. Let's just play with this. Let's just what happens if I change this? What does that change? Does it change a lot or a little? In this case, changing the equation changed a lot. But sometimes it doesn't. We're going to do that all the time in this class. And that's really where the fun is. And then the last thing I want you to understand is that not all math questions have answers. Math isn't this thing that we did and it's done and it lives in this book and that's it. There's so much that we don't yet know. It is not that long ago that if I would have been making this video, I would have had to say, yep, we still don't know the answer to this question. And there are a lot of things out there that we don't have answers to. If you Google the Millennium Prize problems, you'll see a list of these kinds of math questions that we don't have the answer to, that it drives us crazy that we don't have the answer to them. And so anyone who solves them will win $1 million. There is $1 million prize for the solution to these problems because we don't know the answer. I won't give you questions in this class that don't have answers, but I think it's important that you know that those are out there, that you're doing something that is a real, active, living field. And I hope you can find some joy and some fun in that. And I'm really excited to take you on this explorative, hands-on mathematical journey.